In this video, we're going to look at another example of Taylor series and Maclaurin series. The question here is to find the Maclaurin series for the function f of x is equal to sine x, and also find the radius of convergence. Part B. By differentiating the Maclaurin series for sine x obtained in exercise A, find the Maclaurin series for g of x is equal to cos x. So for part B, we're looking at the derivative of sine x, which is cos x. So once we find the Maclaurin series of sine x, we're just going to differentiate it, and by doing that, we can find the Maclaurin series for cosine x. All right, let's do part A first. So we have f of x is equal to sine x. Plug in 0 for x, we get f of 0 is equal to sine of 0 is equal to 0. Now differentiate f prime of x is equal to cosine x. Plug in x equals 0, f of 0, f prime of 0 I should say, f prime of 0 is equal to cos of 0. What is cosine of 0? Cos of 0 is equal to 1. Now differentiate again, f double prime of x. What is derivative of cosine x? That's minus sine x. Now plug in 0. F double prime of 0 is equal to minus sine of 0. Sine of 0 is equal to 0. Now f triple prime of x. F triple prime of x. Differentiate minus sine x, we get minus cosine x. Plug in 0 for x, we get f triple prime of 0 is equal to minus cosine of 0. Cos of 0 is equal to 1, so we get minus 1. All right, let's do the fourth derivative. The fourth derivative is going to be derivative of minus cosine x would give us minus times minus sine x, because derivative of cos x is negative sine x, double negative is a positive, so the fourth derivative is just going to give us sine x. Now plug in 0. F fourth of 0 is equal to sine of 0 is equal to 0. Now the fifth derivative. The fifth derivative of x, derivative sine x, is going to give us cosine x. Plug in x equals 0, and we get f5 of 0. The fifth derivative at 0 is equal to cosine of 0 is equal to 1. So let's now list the derivatives so we can construct the Maclaurin series of sine x. So we have f of 0 is equal to 0. We have f prime of 0 is equal to 1. F double prime of 0 is equal to 0. F triple prime of 0 is equal to negative 1. F fourth of 0 is equal to 0. And the fifth derivative, f fifth of 0, is equal to 1. All right, notice that the even derivatives, f of 0 is equal to 0, f double prime of 0 is equal to 0, and the fourth derivative at 0 is 0. They're all zeros. But the odd derivatives, they alternate between 1 and minus 1. So let's write down the formula for the Maclaurin series. F of x is equal to f of 0 plus f prime of 0 times x plus f double prime of 0 times x squared divided by 2 factorial plus f triple prime of 0 x cubed divided by 3 factorial plus f fourth of 0 x to the 4 divided by 4 factorial, and so on. Now let's plug in values for these derivatives. F of 0 is equal to 0. F prime of 0 is equal to 1, so we get 1 times x. F double prime of 0 is equal to 0, we get 0x squared divided by 2 factorial. F triple prime of 0, that's going to give us negative 1, so we get minus x cubed divided by 3 factorial. F fourth of 0 is 0, x to the 4th divided by 4 factorial. And f5 of 0, the fifth derivative at 0 is equal to 1, so we get 1 x to the 5 divided by 5 factorial. So let's simplify this. All the even terms collapse. All the even powers of x are zeros, so they collapse. So we get x, only the odd powers of x remain. And that's intuitively clear because sine x is an odd function. So we get x minus x cubed divided by 3 factorial plus x to the 5 divided by 5 factorial and minus x to the 7. So we see the pattern. They go up by 2 starting at x, so we get x minus x cubed over 3 factorial plus x to the 5 divided by 5 factorial minus x to the 7 over 7 factorial, and so on. So this is the Maclaurin series of f of x is equal to sine x. All right, so we have sine x is equal to x minus x cubed divided by 3 factorial plus x to the 5 divided by 5 factorial minus x to the 7 divided by 7 factorial, and so on. Now, we need to generate odd powers of x. So let's let n be equal to 2k plus 1. So we can write sine x, we can write the Maclaurin series of sine x as summation k equals 0 to infinity minus 1 to the power of k. This is because the odd powers of x alternate between 1 and -1, and -1 to the k alternates between 1 and -1. And we need odd powers of x, so we're going to get x to the power of 2k plus 1 divided by 2k plus 1 factorial. This is the pattern of the general term. It's a formula for the Maclaurin series of sine x. So now that we have the Maclaurin series of f of x equals sine x with center a is equal to 0, now that we've developed the pattern for the general term of the Maclaurin series, let's apply the ratio test to find the radius of convergence. All right, so let's do the ratio test. We have limit k approaches infinity, a sub k plus 1 divided by a sub k. This is equal to limit k approaches infinity, absolute value of -1 to the power of k plus 1, x to the power of 2 times k plus 1, increase the value of k by 1, plus 1, divided by 2 times k plus 1, plus 1, all factorial, all divided by a sub k, which is -1 to the power of k, x to the power of 2k plus 1, divided by 2k plus 1 factorial. So let's simplify this. We get limit k approaches infinity, absolute value of -1 to the power of k plus 1 divided by -1 to the power of k, x to the power of 2k plus 2 times 1 and then plus 1, so we get 2k plus 3 divided by x to the power of 2k plus 1, and we get, in the denominator, we get 2k plus 2 plus 1, so we get 2k plus 3 factorial, and in numerator, we're basically flipping this term, we're reciprocating it, so we get 2k plus 1 factorial, flips and comes out in the numerator. All right, so let's simplify this. We get limit k approaches infinity, absolute value. Now, -1 to the power of k plus 1 divided by -1 to the power of k, we have the same base, subtract the exponents, so we just get -1. And x to the power of 2k plus 3 in the numerator, and we have x to the power of 2k plus 1, same base, subtract the exponents, and we get x squared. Now, in the numerator, we have 2k plus 1 factorial. So let's rewrite the denominator as 2k plus 3 times 2k plus 2 times 2k plus 1 factorial. The reason we do this is because we want 2k plus 1 factorial to cancel from the numerator and denominator. Now let's get rid of the absolute value. The absolute value of -1 is just 1, so x squared is always positive, so we get limit k approaches infinity, x squared divided by 2k plus 3 times 2k plus 2, and this limit will be 0. Why is that? Because x squared is a fixed number divided by the denominator, which is approaching infinity, because k approaches infinity. The denominator approaches infinity, and a fixed number divided by infinity, the ratio will approach 0. So that means that the radius is infinity, and the interval of convergence is between infinity and minus infinity. All values of x. This series converges for all values of x. All right, since the radius of convergence is r equals infinity, the interval of convergence is from minus infinity to infinity. Part B. find the Maclaurin series for g of x is equal to cosine x, and we're going to differentiate the Maclaurin series for sine x to find the Maclaurin series for cosine x. So in the first, in part A, we found the Maclaurin series for sine x as summation n equals 0 to infinity, negative 1 to the power of n, x to the power of 2n plus 1 divided by 2n plus 1 factorial. We can write this in expanded form, so we get sine x is equal to x minus x cubed divided by 3 factorial plus x to the power of 5 divided by 5 factorial minus x to the power of 7 divided by 7 factorial, and so on. So now we can just differentiate both sides and find the Maclaurin series for cosine x. Differentiate sine x as the left-hand side, we get cosine x. Differentiate right-hand side, derivative of x is 1. Derivative of x cubed, apply the power rule, so we get 3x squared divided by 3 factorial plus 5x to the 4th. Apply the power rule, divide by 5 factorial minus derivative of x to the 7 will be 7x to the 6. Apply the power rule, divide by 7 factorial, and simplify. So if we simplify this, we get cosine x is equal to 1 minus x squared divided by 2 factorial plus x to the 4th divided by 5 factorial. Sorry, x to the 4th divided by 4 factorial minus x to the 6th divided by 6 factorial. How are we getting, say, 6 factorial here and 4 factorial here? Let's show that. So let's show it for this term here, for example. We have 7x to the 6th divided by 7 factorial. Well, we could write the denominator, 7 factorial, as 7 times 6 factorial. And in numerator, we have 7x to the power of 6. The 7 cancels out, and we get x to the 6th divided by 6 factorial. So that's the same thing holds for all the other ones. All right, so another way of getting the Maclaurin series of cosine x is to differentiate the compact series for sine x. So let's also do that. So we have sine x is equal to summation n equals 0 to infinity minus 1 to the power of n, x to the power of 2n plus 1 divided by 2n plus 1 factorial. The advantage of this method is that we get a formula right off the bat for a Maclaurin series of cosine x. We don't have to guess the pattern because we just differentiate the formula for the Maclaurin series of sine x to get a formula for Maclaurin series of cosine x. Differentiate the left-hand side. We get cosine x. Differentiate the right-hand side. The only thing that gets differentiated is the variable part, which is x to the power of 2n plus 1. Everything else is a constant, so we just rewrite them. Negative 1 to the power of n. Differentiate x to the power of 2n plus 1 using the power rule. We get 2n plus 1. Subtract 1 from the exponent, x to the power of 2n. Divided by 2n plus 1 factorial. Now, let's do some simplification. We have 2n plus 1 in the numerator. In the denominator, we have 2n plus 1 factorial, which we can write as 2n plus 1 times 2n factorial. And the 2n plus 1 cancels out, and what do we get? We will get just 2n factorial in the denominator. So we get 2n factorial in the denominator, and in numerator we have negative 1 to the power of n times x to the power of 2n. And of course, don't forget to put the summation. So let's put that in, let's squeeze it in. That's summation n equals 0 to infinity. And let's put the equal sign here. So this here is the Maclaurin series for cosine x. Let's rewrite that, cosine x. And we got that by differentiating the Maclaurin series for sine x that we had developed earlier in part A. Cosine x is equal to summation n equals 0 to infinity. And it's easy to memorize because cosine x is an even function, so it has only even powers of x for its Maclaurin series. Negative 1 to the power of n, x to the power of 2n, divided by 2n factorial. All right, so we now have the Maclaurin series for g of x is equal to cosine x. That's summation n equals 0 to infinity minus 1 to the power of n, x to the power of 2n, divided by 2n factorial. This is the Maclaurin series for cosine x. What about the interval of convergence? The interval of convergence is not affected by differentiation or integration. Only convergence at endpoints can change. But we don't have endpoints. the interval of convergence for sine x was minus infinity to infinity. Since we don't have any endpoints, the interval convergence for cosine x will also be minus infinity to infinity. And cosine x can be represented by this Taylor series or Maclaurin series, summation n equals 0 to infinity, negative 1 to the power of n times x to the power of 2n divided by 2n factorial on the entire interval from minus infinity to infinity. This is the interval of convergence. So the interval of convergence is all values of x. For all values of x, we can represent cosine x by this Maclaurin series. All right, thanks.